Let me, you guys enjoy the break?
Yes.
Yes. All right. Well, let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Thank you for the break and the time to refresh and get back on track, hopefully. And just pray you be with these students, help them each day, Lord, as they study this course, that you would just guide their steps, help them to find help when they need it, and just encourage them to just do their best, Lord, each day for your glory. I just pray that you bless this class. Just, again, let us understand what we need to do today and help the students to ask good questions as they have them, Lord. In your name I pray. Amen. All right, so any questions while I'm finding my markers? So I gave you guys an assignment, right? And so I hope you have seen the assignment and worked on it. It's not that complicated. Pretty much to do the assignment, all you need to do, right, is to watch the video that I posted last Wednesday on long division, right? I have 2 videos. I go through, I forget, 10 or I forget how many examples, a bunch of examples, right? A long division and what it means, right? So yeah, there's 2 things with long division. The one thing is, how do you actually do it, right? And then the other thing is, what does it tell you about the polynomials in question, right? So I will, well, we'll be doing more long division as we need to in examples going forward. So I'll just say that. Is there any questions about those videos? Feel free to ask now. No? Okay, so I want to talk about sort of reverse problems for just a few minutes. So basically here's the general theme of this is given some data about a polynomial, you know, f of x, let's say, create a formula to reproduce the data. So this is, I say it's reverse because up until now, what's the format we've been working with? The format has been what? I say, here's a formula for f of x, right? Let's graph it. So now I'm turning the tables. I'm saying, how do you find a formula that has certain features, right? So example 1, find polynomial of least degree with graph below. All right, so let me give you a graph. Here we go. Bounce, cross, cross, then bounce. So here's the graph. All right. Let's suppose that this bounce happens at -6. Let's suppose this crossing here happens at 4. Let's suppose this bounce over here happens at 10. And let's additionally suppose that the y-intercept is 30. All right. So how do you approach a problem like this? So I'm just gonna do it. All right, I'll show you, and I'm gonna do one, and then I'm gonna let you guys think harder about the next one. Okay. So this one, what we want to do is we want to leave a constant in front to adjust for the sort of vertical scale. So we'll call that constant A. We don't know what it is yet. All right. I want it to bounce at -6, and I want it to do so with the least degree possible. So the smallest degree thing you could make that happen with is an x plus 6 squared. All right, that'll give me a bounce at 6, that being in the formula, right? To get it crossing at 4, the easiest way to do that is just to put an x minus 4, right? like that. That'll give me a crossing at -4. And then I get a bounce at 10, right? So to get that, I want an x minus 10 squared, right? So this will give me a polynomial that, roughly speaking, looks like this, right? Now, how do I figure out what a is? Well, that y-intercept should tell me what the a should be. So how do I figure that out? Well, f of 0 is what? F of 0 is 30, right? But it's also equal to a times 6 squared, which is 36, times -4 times 100, right? Because minus 10 squared is 100. Yep. Why is the 10 squared? Ah, good question. So the difference is in the graph. At 6, we got a bounce, right? At -6, there's a bounce. At 10, there's also a bounce. That's why we want the square, to make it bounce off the graph. In contrast, the 4, there's a crossing. So x minus 4 will do that. I mean, you could put an x minus 4 cubed there. It would look similar. But then it wouldn't be least degree, right? So x minus 4 is the smallest degree thing I can get to get that crossing. So that's what I want to do. And now you multiply it out. What do you got? Oh. Oh. Big number.
You put 30 in for all the x values, right?
No. This is where x equals to 0. So 30 should be equal to f of 0 should be equal to 30. That's the y-intercept. I don't have any information about what happens when x is 30. That was not given. Okay, so 36 times 4 is what, 120 plus 24, which is 144. So that's minus 144,000. Wait a minute. No, minus, I should say 14,400. Anyway, the point here is a is equal to 30 divided by minus 14,400. And I think we could, I probably should have not multiplied it out, right? It would have been smarter if I just left it as 36 times minus 4 times 100, right? Because then I could have simplified the fraction better. What's that? Yeah. I'm sorry, my children stole my calculator. I'm without calculator at the moment. It's not a good excuse, but it's true. So what'd you get? So this cancels with that 0, so to speak, and that gives you 3 over 36 is 1 over 12. So I think it's minus 1 over 48. Yeah. Am I right? Somebody actually have a calculator? Check me. Is 30 divided by 14,400 equal to minus 1 over 1 over 48? There's a minus too. Yeah. Okay, so put all together. Answer is f of x equals to minus 1 over 48 times x plus 6 quantity squared times x minus 4 times x minus 10 squared. Does that make sense? Let's see if we can do a different one. Yeah? Example 2. Again, find polynomial of least degree with graph below. All right, so this time, suppose it would look something like this. Whee! All right. I'm going to give us this crossing at minus 8. This one is going to be at minus 3. This one's going to be at 2. And I'm also going to give us that this point right here is 1, let's say -3. Find the polynomial of least degree which has this data. So the way to go here, so you guys tell me, what should I make my f of x equal to what? Any ideas? It's all good. Oh, A? Yeah, okay, sure. We can put an A in there. We don't know what that is yet. How do I get this x minus 8 crossing? What do I want to put an x plus 8 in the formula? Yeah. Then what? X plus 3 squared. Now, why did you square that? Because it bounces there. Very good. And then what? X minus 2. All right. Now, okay, so that's going to have the shape that we have, right? Now, we can fix that constant out front with that other piece of information we haven't used yet, which is what? The point 1 comma minus 3 is on the graph. What does that mean? That means that f of 1 is equal to what? -3, right? F of 1 is -3. What is f of 1? It's equal to a times 1 plus 8, which is 9, right? Times 1 plus 3 squared, which is what? 16. Times 1 minus 2, which is minus 1. Does everyone understand? Yep.
You're putting the 1 into x.
Yes. F of 1. We have to evaluate the function at 1. So exactly, I'm putting x equal to 1 to get from here to here. Right? So what is that? That is 9 times 16, which is it's 144 again. What are the odds? Minus 144a. That's funny. And that I said that was equal to what? -3, right? So we got -3 is equal to that, which means a is equal to -3 over minus 144. 144 is like 12 times 12, right? So you got like -3 over 3 times 4 times 12. So those, oh, what? Whoa. Whoa. That's an accident, folks. Whoa. Dude. Please don't let, I mean, if there's a mistake, I don't even want to know about it. Huh, funny. The answer to A is not always minus 1 over 48, okay? That's an accident. Suppose 1 comma 0, 3 comma 0, 4 comma 0 are points on the graph of y equals f of x, where f of x is polynomial. All right. If 2 comma 10 is also on graph, find polynomial of least degree satisfying these conditions. All right? So this time just words. I didn't give you a picture, right? So how do we get an x-intercept? These are all x-intercepts, right, except for the 210. So from the factor theorem, right, from the factor theorem, we should do what? F of x equals to what here? Let's put an a in there because we want to be able to adjust it, right? So f of x equals to a times what? To get the 1, 0 in the graph, we do what? We put an x minus 1, right? The factor theorem says put x minus 1 there. To get the 3, 0, we put an x minus 3. Yeah? To get a 4, 0, we put x minus 4. And do I want any of these to be, why don't I want any of these to be squared? Right? They're x-intercepts, I mean, they could be squared, but then what? They could bounce. Why? But I mean, in principle, they could bounce. In practice, why don't we want that? Because what's the instructions? Polynomial of least degree, right? So whenever you have a bounce, that's a degree 2 thing, right? So that's a luxury we don't want to afford here because we're looking for the polynomial of least degree, which has these 3 points on the graph. Well, and that 4th point, right? So that's the least degree polynomial, which has those x-intercepts. Of course, you could take any one of these and square it, and it would still go through those points, right? But it wouldn't be the polynomial of least degree. It'd be a higher order one, right? Everybody top-hatted? I got 26. 3, 4, 5, 6, 7, 8, 9, 10, 11, 15, 16, 17, 18, 19, 26, 27, 28. I think that means, oh, there we go, 28. Some of you heard me. Okay. So I hate to shut that thing and then people, I wasn't on the top hat. All right. What is it? What'd I do? No? So then what? Yep. Something with that 2. How do we use that? What does that mean for the point? Plug in for x. So 210 on the graph, right? So we know f of 2 is equal to 10, right? The input of 2 gives us the output of 10. So that will tell us what the a should be. So so we have 10 is equal to f of 2, but what is f of 2 equal to? It is equal to a times 2 minus 1 times 2 minus 3 times 2 minus 4, right? Just like the last one, we plug x equal 1 into it. Now we're plugging x equals 2 into it. What does that give you? 10 equals 2. So this is minus 1. Wait a minute. What? No, this is 1, minus 1. This is minus 2. So what do you got? You got, I think I got 2. All right. So this is a times 1 times minus 1 times minus 2, right? So what you have is 2a. So therefore, a is equal to 10 over 2, also known as 5. And the answer is simply f of x equals to 5 times x minus 1 times x minus 3 times x minus 4.
How do we know there's no bouncing?
Because, well, we're not given the graph, right? So we're not forced to bounce from the picture. And again, it's least degree, right? So if I put a square in any of these, it'd be degree 4 or higher. That wouldn't be the least degree. So. Any questions? You guys have any questions about the homework? No? All right. Well, in that case, I have another example for us. This one's going to be a little bit different. There are a bunch of, I think there's probably like five problems in the homework that are kind of sort of like these examples, all right? This one's a little bit different. Given parabola with vertex -2, 1, and let's say 3, 10 on its graph. Find formula for f of x. Right, so the parabola, you know, I'm saying that the parabola is y equals f of x, okay? So I want to know what's the formula for that parabola. So how would you solve a problem like this? What's the right starting point for a problem like this? So we know it's a vertex, right? That's a very special point. So that says to me, I should use the vertex form of the parabola equation, right? What's the vertex form of the parabola equation? So we have y equals f of x is equal to a times x minus h quantity squared plus k, right? That's one of those things that should certainly be on your formula sheet, right? The vertex form of the parabola. Okay, so we know what h and k are, though, right? What are they? We don't know what a is right offhand, but we know that h is -2, right? So that makes this x plus 2 quantity squared, right? Plus 1. Well, great, we're almost done then. What do we need now? We need to figure out what a is. How do we figure that out? Just like the previous 3 examples, right? We plug in the data point that we have. What data is that? 3, 10 is on the graph, right? So what does that mean? 3, 10 on the graph means f of 3 is equal to 10, right? F of 3 is equal to 10. How does that work here? So we have f of 3 equal to, ooh, did you pan? Yes. Okay, cool. I was like, wait a minute. Phew, it's good. I am my own worst cameraman, so. Let's see here, so 3 plus 2 is 5, right? So we've got 5 squared plus 1. And that's all equal to 10, yeah? So what that gives us is 25a is equal to 9. So a is in fact equal to 9/25. So therefore, f of x is equal to 9/25 times x plus 2 quantity squared plus 1. And there you go. That is a formula for f of x. Now, what if the instructions didn't just say find a formula? What if the instructions said find the formula in standard form? Would this be the answer? No, because this is not in standard form, right? This is in vertex form. What would standard form? If I add the words in standard form here, you know, that changes the problem a little bit. So to get that, I multiply this out, right? This is 9/25. What's x plus 2 squared? It is x squared plus 4x plus 4. All of that we add 1 to. And so what we have here is 9/25 x squared plus 36 over 25 x. And then I need to add, what's 36/25 plus 1? What's that equal to? What's 36 plus 25? It's 61, so 61/25. And so there you go. That would be the answer in standard form. Now, hypothetical, if this was a problem on your next quiz or test, I would give you like tons of partial credit if you just gave me the vertex form and didn't give me the standard form, right? Because most of the difficulty here is actually finding the vertex form, right? In fact, if you don't have the idea to use the vertex form, this is a really, really hard problem from other ways. Because the vertex is -2, 1. So the vertex here, this is h, k. So h is -2 and k is 1. Uh-huh. So we definitely have time for more examples like we're doing today, but I want to stop here for these kinds of examples today and just let you try the homework. You get stuck on something, you come to class, you ask about it, okay? What I'm going to do now is I'm going to move on to how do we graph rational functions. So I want to get a couple examples of that under our belt here today, because that's really the remaining oh, don't breathe that. It's not good. That wasn't really one of the main points of my lesson plan for today, but it's a good life lesson if you can learn it. I apparently can't because I keep doing this. There's no kind of high or anything either. It's just bad. Oh, I'm sorry. What am I talking about? But example 5. So graphing rational functions. What is a rational function? So a rational function is something like this. F of x is equal to p of x over q of x, where p of x and q of x are polynomials. All right. How do you graph a rational function? Well, the answer is a lot like we graphed polynomials. So what we want to do is step number 1, you want to factor. Well, there's a little bit more fine print here. All right, fine. If the degree of p of x is less than the degree of q of x, all right, then proceed to 2. Otherwise, do long division. Well, great, googly moogly. Tell you what, we don't have enough time today for me to properly state this algorithm. Let me bail on doing this at the moment. It's a bad idea. I'm going to spend 10 minutes writing the algorithm, and then we'll be out of time. It's better for me to do examples today, and then we'll write the algorithm next time. My bad. Sorry, guys. There's a little bit more nuance here, because the issue with whether your polynomial is like a proper rational function or improper, we need to return to that. Let me just get straight into it. Example 1. Suppose we want to graph f of x equals to x squared minus 1 over x squared minus 9. All right? Now this one here, and I'll add an extra x down here for goodness. So the first order of business, much like it was for polynomials, is just to completely factor the thing. So to completely factor this, we've got x plus 1, x minus 1, and downstairs I've got an x plus 3, and x minus 3, right? Now, and then I identify critical numbers, yeah? Identify critical numbers. And so the critical numbers here either come from where the denominator is 0 or from where the numerator is 0, all right? So here, I draw my number line, and let's see, I've got one at minus 3. And I've got one at -1. I've got a critical number at 0. I've got another one at 1. And then I've got another one at 3. I'm attempting some semblance of scale here, okay? Now, we want to put pluses and minuses according to the pattern, yeah? And so how do we get started? Well, think about plugging a really large number into this expression, right? Like, or pick 4 if you want. Plug 4 in there. What happens? What do you get? What happens when we plug 4 into this? Oh, man. Ugh. I get 5 times 4 times 4 times 7 times 1. Those are all positive numbers. We get pluses. All right? The same sign flip theorem works here. So there's going to be a sign flip every time because there's only power 1 here. Every time it flips signs. So we go minuses, we go pluses, then we go minus again, we go plus, and finally we go minus. All right? And that's pretty much what I need to make the graph. Now, a little bit more here. So there's an important distinction between the numbers that appear in the denominator versus the numbers that appear in the numerator, right? The numbers that appear in the denominator give us vertical asymptotes. There's going to be a vertical asymptote at x equals 0, -3, and also 3, right? So those are like here. So I try to use dotted vertical lines to denote the vertical asymptote. My y-axis is a vertical asymptote. All right, like that. And then the other thing here, and this is where the long division issue comes up, but not so much for this one, because the degree of the numerator, all right, is smaller than the degree of the denominator. This is a quote-unquote proper rational function, and so that means the horizontal asymptote is just the y-axis, is just the x-axis. So there's going to be a horizontal asymptote like here. And what that means is that for large or like very large values of x or very large negative values of x, it gets sucked into the x-axis basically. All right, then what? How about the numerator? What does the x plus 1 and x minus 1 tell us? This tells us X-intercepts, right? X-intercepts of -1, 0, and also 1, 0. So that's a place where it crosses the x-axis. So that's like here and here. All right? Now I just have to go through those dots and respect the asymptotes, all right? And here's how it goes. So it's negative over here, so it's got to be below the x-axis, but it goes down like that, all right? Then it's positive over here, like this. Has to cross through the axis right there, and then it goes like that. All right? Then it's positive on the other side of 0, and it crosses that x-intercept there, right? And then we go down. We got this vertical asymptote over here like that. All right? And then up here again, because we're positive, and like that. And there you go. That's the graph of y equals to x squared minus 1 over x squared minus 9 times x. There's a lot in common here with the polynomial graphing, right? But there's some new things. This vertical asymptote thing is obviously new, right? Let's look at another example. Yep.
How did you find the vertical asymptotes?
Wherever the denominator is 0 could be a vertical asymptote. Example, oh, did I say example 1? I'm an idiot. That's example what? 5. It's example 1 of rational functions for what it's worth, but I usually keep numbering for a lecture. Example 6, yep.
You put the dash lines for
Vertical.
asymptotes for the vertical ones there. What are the side
The horizontal asymptote, it's like that.
Oh, okay. So
Yeah.
it's just saying that it can be normal.
Right, right. So here's another one. We could have y equals f of x. Was there a question? No? So make this one a little bit different. So here, I'm going to do x minus 1. Well, let's say x minus 2 over x squared minus 4. Let's graph this thing. All right. So here, something a little bit interesting happens. See, when we factor, what do we get? So when you factor and you've got the same factor in the denominator and the numerator, that we have to treat as another thing. All right, that's a special case. This gives us what's called a hole in the graph. So when you have, see this and this, see how they match? That implies hole in the graph. All right. So away from x equals to 2, right? Everywhere except for x equals to 2, you're just looking at, this is literally equal to 1 over x plus 2, right? This is for x not equal to 2. Do we know how to graph? Do we know how to graph y equals 1 over x plus 2 already? We learned that already, didn't we? Remember that? We take the reciprocal graph. What was it? Reciprocal graph is this guy, right? Y equals 1 over x. And then to get to y equals 1 over x plus 2, what do? We shift left, right? Correct? Oops. My color coding is failing. So that moves, there's a vertical asymptote of the y-axis, right? In the reciprocal graph. We shift 2 units to the right, excuse me, to the left. And our vertical asymptote is at minus 2, right? And our graph looks like this, right? But so this would be the graph of y equals to 1 over x plus 2, okay? But that's not the correct answer yet. I mean, I could put the correct answer up here. So what do we have to, I'll put it down here though, just so you can see the difference. So then, I mean, we've got a vertical asymptote of minus 2, right? And I should be careful. I should be careful here. Oh, yeah, my bad. Well, anyway, you guys can't hear my thoughts, so it's okay. I was thinking about something different, but I didn't say anything about it, so it's okay. Now, so if we look at this, we have degree 1 upstairs, degree 2 downstairs, right? So again, it's got a horizontal asymptote of the x-axis, right? So all we have to do is take the y equals 1 over x plus 2 graph, which is this, right? And what happens? We have to, at x equals to 2, we lose a point. So it's missing, there's a hole in the graph right here. And so that's what this thing looks like. Very silly, but that's what it is. This is the graph of that. Where is the hole? So to figure out where the hole is, use the formula right after. See this formula right here? We can use that formula to figure out where the hole actually is. It would be at 2 comma, we use that formula, 1 over 2 plus 2. So the hole is actually at 2 comma a quarter, for what it's worth. you guys ever see a hole in the graph before? This new? Yeah. So well, I want to punch some more holes in some graphs here. It's not really a big deal, the hole in the graph thing, but I remember the first time I saw it, I was like, huh? What's that? It is something that would I mean, there exist college algebra classes out there which just dodge this issue altogether. But there's no need for that. I mean, it's not hard to talk about. Example 7. Suppose you have find formula for parabola with X-intercepts of, let's say, -2, 0, 3, 0, and y-intercept of 12 with a hole in graph at, all right, you guys pick the number where you want to put the hole. 5? All right, I'll allow it. Okay, so what we're going to start by is producing the parabola. So our parabola, like we were doing at the start of today, f of x is a. To get -2, 0, we do x plus 2, right? To get the 3, 0, we do x minus 3. We want a y-intercept of 12, right? So we need f of 0 equal to 12, but that's a times what? 2 times -3, right? So apparently a is equal to 12 over -6, also known as -2. So we get f of x is equal to -2 times x plus 2 times x minus 3, right? Great. This is all fine and dandy. There's no holes in this, right? The graph of this would just look like what? -2, 3, the x-intercept is 12, so it looks something kind of sort of like this, right? Where's the vertex? Did you guys forget? Where's the vertex? If the x-intercepts are -2 and 5, the vertex is halfway between, right? There's 5 units between those, so 2.5 over. So like the vertex should be like 0.5-ish, here-ish, should be the vertex. All right, anyway. How do I punch a hole in the graph? Let me call that the formula for that g of x. So I mean, I can picture it, right? It's like down here somewhere, put a hole. So to get the hole, I just do the same formula as I already have. And get this, all you have to do, it's exceedingly silly. You want to punch a hole in the graph, you just multiply by x minus 5 over x minus 5. That's all that's going on here. This is a mathematical hole puncher. You just multiply by that thing. It's always equal to 1, except where it's not defined, which is 5. That puts a hole in the graph. You guys want to punch another hole in the graph? We can do it. Like, suppose you want to punch a hole. Want to punch a hole at the origin? Right here? Oh, we don't. We had the intercept there. Let's punch a hole at -1. How would we do that? We just take it and multiply by x plus 1 over x plus 1. So anyway, we just need to be aware of this as we're graphing rational functions, because whenever we have the same factor in the numerator and the denominator, that leads to a hole in the graph, which we have to kind of be aware of. Anyway, that's it for today, guys. So welcome back. Glad you survived the break. I know you were missing math the whole time, so this is, you feel better now, right?